Alright, so this is grade 10 maths. Good morning, and good morning. If you are also in grade 9, you can stay because what we are covering is very similar to the grade 9 syllabus. So if you are in grade 10, if you are also in grade 9, you won't lose out by being here. Alright? So if you are in grade 9, it's okay that you are here, right? So for grade 8, I can't be sure yet. Unfortunately, I can't be sure yet what time I'll be doing grade 8. Because, unfortunately, here at home at the moment, it's a bit crazy. You know how when there's holidays, it's not as I would have liked to have a scheduled and a planned program, but it becomes very difficult for me to commit to a specific time. So for now, the grade 8s will just have to wait until maybe you see me live again, and then, alright. But for now, I can be sure that we can have the grade 10 session now. So if I can have the people that are in grade 10, also if you're in grade 9, being in this session will benefit you as well, because the beginning of the syllabus for both grade 10 and grade 9 is similar. So, how many of you in this live now joined the previous session for grade 10, which I held on Monday? If you were able to join the grade 10 live session on Monday, could you please indicate in the comment section? If you were not able to, please also indicate in the comment section. If you were able to at least go to the YouTube channel and watch that first session that I did, please also indicate that you watched the YouTube video that I uploaded, because the session on Monday, I actually went ahead and uploaded the session. Okay, I say your point up, you were not able, that's fine. But I do want to indicate that if you do miss a session, remember that in the YouTube channel, I upload the session for that specific day. Alright, so I upload that session so that people can have the opportunity of watching it. Okay, alright. But hopefully, if you are joining in for the very, very first time and you didn't have the chance to go check out the YouTube channel, then hopefully today's session, as we go through it, you will be able to also catch up. Alright. Now, firstly, I want to do the corrections for the work that I had posted as homework on Monday. Alright. And in order to do that, I'm just going to post up I think a screenshot of that work. Please do share the live with those grade 10 learners that you know, any of your friends, cousins, relatives that may be possibly going to grade 10 next year. Share this live with them, or friends that you may have. Okay, so from what I can see, there's 6 of us that are here. and hopefully all of us are grade 10, and some of us, if possible, if let's say for instance there's a grade 9 learner who's here, that's also fine, because that's also going to benefit. Queen B, that's fine if you weren't able to attend. Please guys, there's a YouTube channel that I have. It's called Maths is a Game. YouTube channel called Maths is a Game. I upload all the sessions that we do here on that YouTube channel, so that you guys can revisit and go through the session at your own pace, and in that way you do not get left behind. Alright, so if you are joining in for the first time, please do follow the live creator, and also please go to my YouTube channel. It's called Maths is a Game. Maths is a Game. Go and subscribe, so that when I do upload something on that channel that is specific to your grade, you can have the opportunity of getting exposed. Okay. Okay, so I just want to go back and look at what we did before I jump into the exercise that I sent for everyone to do. So what did we do on Monday? On Monday we looked at the real number system. Okay, and we know that the symbol for real number, okay, is given by this letter R. All right. The real number system is divided into two. There's the rational numbers. So the word rational. Okay, let me just wipe the screen here for myself. Okay, there we are. Okay, so the real number system is divided into two. We have the rational numbers and we have irrational numbers. Rational numbers have the symbol Q, right? And then irrational numbers have the symbol Q, but it has an apostrophe. Okay. Then the way that we define rational numbers is a rational number, the letter Q, is any number which can be written as a fraction. Okay, and we need to use an example of A over B, meaning a numerator and a denominator. That's a fraction. Where A, meaning the numerator, and B, meaning the denominator, are integers. Now, integers are simply all positive and negative whole numbers. And by that I mean, if I was to give an example, 0, 1, 2, 3, 4, and so it goes up until infinity. But before 0, there's also -1, -2, -3, and so it goes up until negative infinity. Now, negative and positive infinity simply means that the numbers go on forever. In the positive direction, we can go on 1, 2, 3, 4, 5, 6, 7, 8. Those are all integers. Continuing on, you can count on forever. There's no end. Then -1 before 0, -1, -2, -3, -4, -5, -6. You can count on forever in the negative infinity direction. Those are what we refer to as integers. All positive and negative whole numbers. Those are integers. So we are saying a rational number with the symbol Q is any number which can be written as a fraction. We use A just to denote the numerator and B to give the denominator. Where we are saying A, meaning the numerator, and B, the denominator, are integers. Alright? And by integers we say positive and negative whole numbers. As given in the example, 0, 1, 2, 3, 4, 5, 6, 7, -1, 2, -1, -2, -3, -4. So those are integers. Those are just examples of integers. And B, meaning the denominator, can never, the symbol stands for cannot. B cannot be 0. We cannot have a 0 in the denominator. Alright? So in order for a rational number to a rational number, it needs to be expressed as a fraction where the numerator and the denominator are both integers, but B can never be the number 0. We can't have 0 in the denominator. So if we look at some examples, the number -6 can be written as negative 6 over 1. So is this rational? Yes, it is. Why? Because the numerator is negative 6 and the denominator is positive 1. Both the numerator and the denominator are integers. And we can clearly see that the denominator is not 0, which qualifies this number as a rational number. Okay, so hopefully you guys are getting the drill on what a rational number is. A rational number is a fraction where the numerator and the denominator are what? Are integers. Look at this one. What about 0 over 1, which is basically the number 0? Is this a rational number? Yes. The numerator is 0, the denominator is 1. Is 0 an integer? Yes, it is. Is 1 an integer? Yes, it is. Is 1 0? No, it isn't. So therefore 0 over 1 is a rational number. Look at this one, 7 over 1, which is basically, we can write the number 7 as 7 over 1. Is 7 an integer? Yes, it is. Is 1 an integer? Definitely. So therefore 7 over 1 is what we refer to as a rational number. The denominator is not 0, so therefore this is rational. 12,000. 12,000 over 1. Okay, grade 10 and 9 basically together, grade 10 and 9, because this is applicable for both grades. 12,000 over 1. Okay, Beverly, I hope you are answered. 12,000 over 1 is also a rational number. Why? Because the numerator is a integer, the denominator is also a integer. So therefore 12,000 over 1 also qualifies as a rational number. Okay. So basically, going back to the definition, what is a rational number? A rational number is any number which can be written as a fraction, where the numerator, meaning a, the numerator, is an integer, and the denominator is also an integer. And the denominator, meaning b, can never be what? Can never be 0. So that is one way we can identify a what? A rational number. 10 over 1 is a rational number. Integer, integer, not 0. 21 over 7 is a rational number. Integer, integer, not 0. Negative 1 over negative 3 is a rational number. Integer, integer, not 0. Negative 3 over 6 is a rational number. Integer, integer, and this is not 0. So basically, in other words, we know that rational numbers can be expressed as a fraction. Now, if we go and look at a decimal, how do we express rational numbers as decimals? There are two types of decimals that rational numbers are expressed as. So we're going to look at those forms. The first form of rational numbers, when we express them as decimals, is we can express rational numbers as terminating decimals. What does this word terminate mean? The word terminate means to bring to an end, to stop something. What are we stopping here? Terminating decimals are simply, I'm going to look at an example very quickly. So the word terminate means bringing to an end or stopping something. That's the word terminate. So I want to use a very crude example. So for instance, if someone is pregnant and they terminate the pregnancy, that simply means they bring the pregnancy to an end. It was going, but then when you terminate it, it means whatever month you decide to basically terminate that pregnancy is basically when that pregnancy ends. All right. So let's look at this. Grade 10 and 9. Grade 10 and 9. Terminating decimals are simply the following. We know that 4 over 10 is a rational number, right? But if we were to write 4 over 10 as a decimal, it can be expressed as 0,4. You can grab your calculator if you have a scientific calculator, and you can punch in 4 divided by 10, because we know that this line simply means division. So 4 over 10, if you punch it into your calculator, then you press equal, all right? Or you can basically press a button there. After you've pressed equal, you can press a button there. That's basically referred to, if you have a scientific calculator, it's called the SD button. This is how you basically express a fraction as a decimal. If you press the SD button, it should be there on your scientific calculator. You should then have 4 over 10 expressed as 0,4. Now what do you notice? The decimal number after the comma, you just have a single digit, which is 4. There is no continuation of the number after 4, meaning the decimals terminate, comes to an end, no continuation, no continuation. So 0,4 is a terminating decimal. So that's what we mean by terminating decimal. Hence we are saying that rational numbers expressed in decimal form are terminating decimals. Okay, let's look at another example. 3,14 stop. This is also a terminating decimal. This terminating decimal, we refer to it as a rational number. Let's look at another example. 4,7923 stop. This here, 4,7923. Now there are how many numbers after the comma? 1, 2, 3, 4. But because there's no number afterwards, it comes to a stop. We've terminated the decimal. So therefore that means that 4,7923 is a terminating decimal. So that's why we say rational numbers can be expressed as terminating decimal. That's the first type of decimal that you have for rational numbers. Are we together? Terminating decimals are rational numbers. Why? Because these terminating decimals can be expressed back as a fraction. 4 over 10. You can express this terminating decimal as a fraction, which is 4 over 10. You can express this terminating decimal as a fraction. This actually becomes, and I'm going to show you, if you move the decimal from here, you move it until the end of this number, which is the end, because there is an end. If you move it, it basically is 1, 2, 3, 4. How many times did we move? 4 times. That means the fraction is 47923 over, how many times did we move? 1, 2, 3, 4 up until the end. That means we're going to write 1. How many zeros after the 1? 1, 2, 3, 4. We're going to write 1, 2, 3, 4. So this is 47,923 over 10,000. If you write this 47,923 and you divide it by 10,000, remember how many decimals did we move up until the end? We moved 1, 2, 3, 4. So how many zeros after the 1? 1, 2, 3, 4. So that's 10,000. Okay? So therefore 47,923 over 10,000 is actually a rational number, because remember we said a rational number can be expressed as a fraction where the numerator and the denominator are both integers. So therefore this here from the terminating decimal can be expressed as a fraction where the numerator and the denominator are integers and where the denominator cannot be 0. Are we together? So therefore that's why we are saying terminating decimals are rational numbers, because they can be expressed as a fraction. What about 3,14? We can express this as a fraction too. Let's move the decimal. How many times to the right? Let's move 1, 2. So what does that mean? 314. over. How many times did we move to the right? 1, 2. How many zeros after the 1? 1, 2. So 314 over 100. So this here, this terminating decimal, we've just expressed it as a fraction, where the numerator is an integer and the denominator is a integer. Hopefully we are going together and everyone is on the same page. That is why we say terminating decimals are rational numbers. Okay. Now, before I move on to the second type of decimal where rational numbers are concerned, I need to get an indication in the comment section that we are going together. Are we together? Hopefully, those who have been in the live from the beginning can indicate in the comment section. Are we going together? Okay. So Naleti says we are together. Chloana says we are together. I love it. If we are together, then I can move on to the second type of decimal that we find for rational numbers. Okay. So terminating means what I said to you. Terminate means to bring to an end. 4,7,923 end. 3,14 end. 0,4 end. So numbers, decimals that come to an end. This is applicable for both grade 9 and grade 10. So if you're in grade 9 or you're in grade 10, you are in the right place. All right. Let's move on to number 2. The second type of decimal that we find for rational numbers is the following: recurring decimals. What? Recurring decimal. What does the word recur mean? It means repeat. What is repeating? The number after the comma is repeating. Okay. Uno, if you missed the live on Monday, you can basically go to my YouTube channel and watch the first session I did on rational numbers and irrational numbers. I'm just recapping now on what I did on Monday. All right. This is only the second day of the session because I skipped yesterday. So if you are in grade 9 or grade 10, you can go and watch on my channel, Maths is a Game. You can go and watch those sessions again at your own time and your own pace so that you can be caught up. The name of the YouTube channel is called Maths is a Game. Just like the TikTok page, Maths is a Game. It's got now roughly just over 300 and something followers, and the profile picture is a drawn in pencil face of a particular individual. You can always check that out there on the YouTube channel. Just make sure that you maybe skip the first few minutes. You'll see, man, you'll skip the first few minutes of that video because at the beginning I explain things that are not related, just things about the sessions and other things. Okay, so just make sure you do that if you are a grade 9 or grade 10 learner. Now let's look at this. But if you are here now, you can even grasp what basically I covered in those sessions. If you are here and you've gotten an understanding of what I'm doing so far. So the second type of rational decimal that we get, spicy. The second type of rational decimal that we get is a recurring decimal. What does the word recur mean? It means repeat. So these are decimal numbers that have a repeating, either it could be a single digit that repeats or it could be multiple digits that repeat. So let's first look at when a single digit repeats. So example, if you take 1 over 3 for instance, we know that 1 over 3 is a rational number, right? Because numerator, integer, denominator, integer, denominator is not 0. So this is a rational number. 1 over 3, if you say in your calculator 1 divided by 3, you say equal and then you press SD, you will see that your calculator will give you this 0.33333333333, and you know what? Your calculator actually brings this 3 to an end, but you know what? If we were to actually extend the length of your calculator and maybe extend it and open more spaces, more decimal placeholders, you would actually find that, hey, This 3 is ongoing. It's a recurring 3, and it is infinitely recurring. So I'm just going to add this word because this is in English an adjective that describes how this number repeats. It's an infinite recurring decimal. What does the word infinite mean? It means no end to the repetition. What does infinite mean? Infinite means forever and ever and ever, no end, no stop. So the word infinite means no end, no stop, forever and ever we are going on. So infinite recurring means repeating without an end. So what are we repeating? We are repeating the number after the comma. If it's a single digit in this case, it repeats forever. So we have come up with some notation in the maths to basically denote when a digit is repeating. So what we do is we can write a 0,3, but then we put this dot at the top, a shaded dot, to indicate that this 3 is repeating. Obviously, we're not going to be able to write all the 3's that are there, that can ever exist, because it wouldn't have enough space. So what we do is we shorten our writing of the number, and we write 0,3, and then we write a dot at the top to indicate that this single digit repeats infinitely. Or we can write 0,3 and we write a line at the top to indicate a repetition of the single digit. So hopefully you guys are familiar now with the kind of notation that we use to distinguish that a decimal is what? It is infinitely recurring, right? So recur means repeat. Infinite means without an end. We are repeating 3 with no end in sight. Repeating 3. Then we use the notation. Course, see, this is grade 10 or grade 9. So if you are in grade 10 or grade 9, you are here. You are in the right place. 3 repeats. 3 repeats. So we put either the shaded dot at the top to indicate repetition, or we put a line over 3 to indicate repetition. Both these notations are acceptable to indicate repetition, either the line or the shaded dot on top of the 3. Hopefully that makes sense. Are we together? Then what I want to say further is that the repetition can either be a single digit or recurring decimals that have a recurring pattern of multiple digits. In other words, not just one digit repeating, but multiple digits repeating. An example of this, look at this number. This is a fraction 2 over 11. We already know 2 over 11 is a rational number, but expressed as a decimal, 2 over 11 is expressed as, it can be written as 0,18. Look at the repetition. If you put 2 divided by 11 into a calculator, or 2 over 11, and then you press SD on your calculator, you will get 0,18181818. Basically, I'm going to write dot 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 to indicate this 1818 pattern repeats indefinitely, infinitely. So what we do is we use either the line, or we could have said 0,18, and what do we put at the top of the 1? The shaded dot. Up on top of the 8, the shaded dot. Either the line to indicate 18 repeats, or the 2 dots on top of the 1 and the 8 to indicate repetition. Okay, any questions, guys? Any questions so far? Any questions of clarity that you have? Are we seeing this difference between, or are we seeing how rational numbers, the 2 ways that rational numbers can be expressed as decimals, either as terminating decimals, 0,4, stop, no continuation, when decimals come to an end, 3,14, 14, stop, terminate, 4,7923, stop, end. These are basically terminating decimals. This is one type of rational number that we get. The second type is infinite recurring decimals. In other words, decimal numbers that basically have a repeating either single digit after the comma, or we can have multiple digits recurring or repeating after the comma infinitely. So, sir, we put a dot on each number after the decimal if it's recurring. Yes. Or you can identify a recurring decimal by seeing the dot on top of that number. Okay? Because that is basically a way in which we are able to write the number without having to write that number all the way through. Does that make sense? So, Naledi, you are spot on, correct. All right. So, very important then, this very important note. Thank you so much. I think you guys are on the same page. If you are asked to identify whether a number is rational or irrational, okay, remember we have not explained what irrational numbers are. But obviously, if we are saying rational numbers can be expressed as a fraction, where the numerator and the denominator are integers, and the denominator cannot be zero, and as decimals it can either be terminating or recurring, then it means the opposite is true for irrational numbers, because irrational means the opposite of rational. It means these numbers cannot be expressed as a fraction, where the numerator and the denominator are integers, and where the denominator is zero. And the opposite then is true, that irrational numbers are non-recurring, meaning they do not repeat, and they are non-terminating. Non-recurring and non-terminating. Okay, so very quickly, let's look at irrational numbers. We looked at rational numbers, so it's only proper that we look at irrational numbers. What are they? These are numbers that cannot be written as a fraction with the numerator and denominator as integers. Okay, so let's look at an example. For instance, look at the square root of 2. The square root of 2 can be written as the square root of 2 over 1. Is the square root of 2 an integer? No, it isn't. Is 1 an integer? Yes, it is. But together, can we say this is a rational number? No, it isn't. If you take your calculator and you punch in the square root of 2 over 1, I want someone to actually do this and punch into their calculator the square root of 2 and then say equal. And then after that, press the button SD, and I want someone to tell me what do they get, what is the decimal number they get from their calculator, so that we can look at the types of decimals that irrational numbers can be expressed as. Irrational, 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 irrational numbers. Okay. So I'm waiting for someone to type for me the number that they get on the calculator for the square root of 2. Square root of 2, you say equal, then you press this button S with the arrow D, SD. This is how we convert this to a decimal number. And I want you then, after you have gotten your answer, to please type in the comment section what that number is, so that we can look at the type of decimal number that an irrational number is expressed as, so that we can distinguish the difference between the terminating decimals, which we said rational numbers have, and the infinite recurring decimals that we said rational numbers have. Okay. I'm very sorry for the noise. You know when they come and fetch trash in the morning, it's that noise, so forgive me. So waiting for someone to punch into their calculator what the square root of 2 is. What do they get? and type in the comment section. Let me know. Anyone? Thank you, Rowan. Really appreciate it. You are the bomb. 1,4142,135,6237. Look at this. So first and foremost, sure. Yeah, someone is really annoying me with the noise. Anyways, so 1,4142,135,6237. If you look at the decimal, all right, your calculator basically has how many numbers after the comma? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 numbers after the comma. But if your calculator had more space to accommodate more placeholders, you would see other numbers after the 7. Okay, going on forever and ever, having no end. Okay, so this speaks to something that we refer to as non-terminating. In other words, if we say non-terminating, the word terminate means to stop, but if we're saying none means not to stop, meaning these numbers go on forever and ever. There is no termination. But at the same time, there's non-recurring. In other words, there's no repetition of numbers after the comma. Do you see a repetition of either a single digit or multiple digits after the comma? Look at this. This is 4142,135. There's no pattern of repetition here. All right? So that's why we say these decimals are non-terminating, no stop. Sorry, guys. Okay, sorry about that noise again. So this is non-terminating decimals and non-recurring. Okay, non-terminating, non-recurring. So non-terminating and non-recurring decimals speak to the numbers being irrational. Okay, all right, non-terminating and non-recurring at the same time. Non-terminating, non-recurring. I want you to take the square root of 3 and I want you to put it in your calculator and then press ST. Take the square root of 3, put it in your calculator, press ST, and I want you to check the decimal number makeup of the square root of 3. And then you can type in the comment section and let me know what you get. What a noise. Freaking hell. Thank you, N. Okay. Square root of 3 is 1,732,050,808. So the decimal. Thank you so much, guys. Naledi and N, I really appreciate it. So look at the decimal. Okay. The day before yesterday, Spicy. It was posted the day before yesterday, which was Monday night. You'll see grade 10 real numbers on the Matters a Game channel. Grade 10 real numbers. Okay. So square root of 3 is equal to 1,732050808. So if we look at the nature of the decimals, like I said, how many numbers after the comma? 1, 2, 3, 4, 5, 6, 7, 8, 9. In actual fact, there would be more numbers that would continue to be there, but it's just that your calculator does not have enough space. So this is also a non-terminating, meaning no stop, and non-recurring decimal. Okay, Isipile, you are spot on. So this then is a irrational number because it's not stopping and it's not repeating. Non-termination just means not stopping. Non-recurring means not repeating. Okay, grade 9 and grade 10. Pi, spicier than I don't know. Okay, because it is there. All right, it is there. It is there. It is there. It is there. I don't know why you can't get it. Yeah, this is basically how it looks like. Did you find the channel though? The YouTube channel, Maths is a Game. Because if you go to my bio and you go to my bio and then you go to the YouTube icon that's on my bio, you click on it, it should send you directly to the YouTube page. The last 3 recent videos that I uploaded on my YouTube channel are the grade 8 video that I did of the Maths Live on Monday, the grade 9 video that I did of the Maths Live that I did on Monday, and then the grade 10 video that I did of a Maths Live that I did on Monday. That's all on my YouTube channel, Maths is a Game. You should be able to find it there. Okay. Yeah, this is basically how it should look like. Basically the thumbnail of the video is of this nature. Okay, so the square root of 3, non-recurring, non-terminating. The square root of 2, non-recurring, non-terminating. There's a symbol in your calculator that we refer to as pi. Pi is also a irrational number because when you press SD after punching in pi in your calculator, you should see a non-recurring and non-terminating decimal, as well as 1 plus the square root of 5 over 2. That's also a non-recurring, non-terminating decimal because there's a irrational number. So whenever there's an irrational number in the mix, that will basically make the entire fraction non-recurring and non-terminating. But you'd always have to check, punching into your calculator, pressing SD, and then checking the type of decimals that you should have that are showcased in your calculator, so that you can be sure based on the decimal. Okay, I'm glad you found it spicy. So I hope you guys are now on the same page with me and you can distinguish between a rational number. Remember, rational number can be expressed as a fraction where the numerator and the denominator are integers, but the denominator can never be 0. And when you look at the decimals, rational numbers have terminating decimals. Numbers come to an end after the comma. Numbers come to an end after the comma. They don't go on forever. Or it can be infinite recurring decimals. In other words, numbers after the comma either repeat infinitely, it can be a single digit that repeats, and we use a dot and a line to indicate the repetition of that particular number, or it can be multiple digits that repeat after the comma, numbers repeating, or it can be 3 numbers that repeat, it can be 4 numbers that repeat. It depends on the type of recurring decimal you have. Then irrational numbers cannot be written, all right, as a fraction where the numerator and the denominator are integers, all right. And when we look at their decimals, we can see that their decimals are simply non-recurring and non-terminating. Okay, So that's just a summary, guys, of the difference between a rational number and a irrational number. So if I was to put some examples here, I have the square root of 2, I have the square root of 3, I have pi, and many other numbers. Okay, Mars, I cannot answer that question because, like I said, it's a bit crazy here at home. I can't be specific. You guys are just going to have to check in when I go live. You know, I can't have a specific set schedule, unfortunately, because of how crazy it is here at home at the moment. This is grade 9 or grade 10. So if you're in grade 9 or grade 10, being in this live is actually, you are in the right place. Square root of 2, square root of 3, pi. Those are irrational. In rational numbers, I explained that rational numbers, you know, we explain the decimal and everything that's attached to that. Okay, all right. Then on my homepage, I did post some homework for grade 10s that they were supposed to have done, where in that basic page, I asked them to basically answer the questions. The questions that were there were state whether the following numbers are rational or irrational or neither. Okay. I think something else that I explained for grade 10s and grade 9s was the difference between what a real number and a non-real number is. Okay. So for real numbers, we know that they can be divided into rational and irrational numbers. So we see the family of both rational and irrational numbers. We have also integers, which are positive and negative whole numbers, all right? 0, 1, 2, 3, 4, 5, 6, negative 1, negative 2, negative 3. Okay, this is grade 10, grade 9. Then whole numbers. Whole numbers are numbers that start at 0. They increase by 1 all the way to infinity. So whole numbers start at 0. 0, 1, 2, 3, 4, 5, 6, and so it goes. All right, those are whole numbers. Then we have natural numbers. Natural numbers start from 1 and they go all the way up to infinity. So whole numbers start at 0, natural numbers start at 1. Integers, on the other hand, extend the whole numbers to basically include the negative numbers. All right, so I repeat, integers, the symbol Z denotes integers. We use the symbol Z to denote integers. Whole numbers, we use the symbol N, and then you could say it's no, but it's N and there's a 0 as a subscript. Then natural numbers, we use the symbol N to denote natural numbers. So natural numbers, like I said, they start at 1 and they increase by 1 up until infinity. Whole numbers, they start at 0. They increase by 1 all the way to infinity. Integers, on the other hand, they are your family of whole numbers, which is 0, 1, and so it goes. But then it also includes your negative numbers. So integers, positive and negative whole numbers, increase and decrease by 1. Whole numbers start from 0, increase by 1. So it's 0, 1, 2, 3, 4, 5, and so it goes. Natural numbers start at 1 and increase by 1 all the way to what? To infinity. So those are integers, positive and negative whole numbers, increase and decrease by 1. Whole numbers, those are numbers that start from 0, increase by 1. And then natural numbers, those are numbers that start at 1 and increase by 1. This here is the entire family of rational numbers. Rational numbers include integers, whole numbers, and natural numbers. Okay? And then I explained what rational numbers are in and of themselves, and the type of rational numbers, and the way that rational numbers can be expressed as decimals to basically include terminating and recurring decimals. We looked at those specific examples. Irrational numbers, on the other hand, are non-terminating and non-recurring when we look at their decimals. Then we have a special type of other number that we call non-real. Non-real numbers are numbers that even root of a negative number. The even root of a negative number. What do we mean by that? The even root. Now we know the roots, right? The even root of a negative number, right? The even root of a negative number. What do I mean by that? Here's an example. The square root of negative 2. The square root of negative 2. This here, if you put it in your calculator, will give you maths error. This maths error simply means that the number is non-real. Okay? Remember that for your square root, this is like saying your second root. This number is even, hence we say the even root of a negative number. So any even root of a negative number is actually non-real, or we use the word imaginary number. So it's either we say this is a non-real number or it is an imaginary number. Imaginary. Okay. Here's another example. The fourth root of negative 25. So let's look at the definition. We said the even root. Okay, is this root even? Yes. The 4 here is an even number. So this is an even root. The even root of a negative number. Is this a negative number inside the root? Yes. So therefore, if you punch into your calculator, you also get maths error. But this maths error means this is an imaginary number. In other words, it's a non-real number. Okay. So all even roots of a negative number are what we refer to as non-real numbers or imaginary numbers. Okay. I hope we are together there. Okay. So that's why we need to understand the definition of a non-real number. The even root of a negative number is non-real. Okay. So when you are asked to distinguish between real numbers and non-real numbers, this is your real number system. Rational and irrational numbers are your real numbers. But your non-real number system includes all even roots of negative numbers. Okay, and I've given you some examples. Is this root even? Yes, because this is the square root. Okay, typically if we are saying the square root, we don't write, for instance here, we don't write the 2. But I just want to write the 2 so that you guys can understand that the square root simply means that there is a 2 there. We don't usually write it down, but that's why we say this is an even root. The fourth root is an even root. The 8th root would be an even root. The 10th root would be an even root. The 12th root would be an even root. And as long as there's a negative number inside that root, then we can say that that number is non-real. Okay. This is grade 10. Also grade 9 would benefit from this. Okay. Are we together? Are we understanding? Odd root? No, odd root. So an odd root of a negative number. Look at it. What did I say? A non-real number is the even root of a negative number. An odd root is not non-real. If you were to say this cube root of negative 4, you are going to get an actual number, which either qualifies this number as a rational number or an irrational number, which would mean an odd root will always be a real number. Okay, can someone take their calculator and put in what the cube root of negative 4 is? Okay, because remember, this is an odd root. Thank you for asking that question, by the way. And the cube root of negative 4, or you could say the cube root of negative 27. Can someone put in the cube root of negative 4 in their calculator and then find out for me what do they get from their calculator? Remember, when you put this in, all right, there is that button that's like this. I think if you want to actually get it from your calculator, you need to say shift, and then you go and press that button that has this yellow thing there. You press that button, you put in the 3 here, and then you put in the -4 there. Alright, and then you press equal, and then after you press equal, you press, if there's no decimal that comes up, you press SD, alright, in your scientific calculator. And then someone can just tell me what do they get from their calculator for the cube root of -4, so that then I can go to the real number system and then place it either as a rational number or as an irrational number. I can classify it in the real number system. But all in all, what I'm saying is that any odd root that has a negative number will always be a real number. It won't be non-real. Okay, non-real numbers are all the even roots of a negative number. If you have an even root of a negative number, it will always be non-real. But if it's an odd root of a negative number, it will fall in the real number system, not the non-real number system. Are we together? So, good question. Whoever asked that question is a very good question. Naomi, good job, Naomi. That was a very good question. Okay, so I'm waiting for someone to basically answer me what is the cube root of -4 in the comment section. I believe it's a negative number, but it's a negative decimal. Okay, hopefully you guys get the point anyway, so I'm just gonna let it go because I can see no one's answering me in the comment section. Okay, so I then had given you homework and I just wanna go over it a little bit here. This homework was saying you need to state whether the following numbers, then look at the even root of a positive number, the even root of a positive number. So the square root of 7, for instance, all right, and the square root of 25. These will all, if it's an even root of a positive number, then that will be rational. I mean, that will be real. It will also fall under the real number system. Okay. But the type of real number that it will be, whether it's rational or irrational, will depend on the decimal. Okay. So, babes go forever. An even root of a positive number will fall under the real number system. All we need to understand is that non-real numbers will always be the even root of a negative number. The even root of a negative number. That will be non-real or imaginary. Everything else that does not fall in the scope of this definition will fall under real numbers. Okay? And real numbers are either rational or irrational. Okay? Yeah. Okay, so I'm gonna move on, guys. Thank you so much for your questions. Your questions are very good. Thanks, Babeska forever. That's quite a name. State whether the following are rational, irrational, or neither. And most when they say neither, it means it's not rational, it's not irrational. Okay, so let's look at this very quickly. The first question that was asked is 0.25. Okay, and then I said, please give me reasons. Why do you say so? So, quick question, guys. 0.25. Is 0.25 rational? Is it irrational? Or is it neither? Okay. Let's see. And please give me a reason. This is a decimal, not 0.25. Okay, thank you so much. Rational. Do we all agree that not 0.25 is rational? Okay, it seems like we all agree. Okay, I have 2 people that are saying rational. Are you sure, guys, it's rational? Okay, yes, guys, this is rational. And remember, we said rational numbers can be expressed either as terminating decimals or recurring decimals. So this one is a typical terminating decimal. It's a typical terminating decimal because the numbers after the comma, they come to an end. They stop. There's no continuation. So this is a terminating decimal, which means this is a rational number. We can even write this rational number as a fraction. If we move the decimal 2 times, 1, 2, we get a whole number, which is 25. And then 1, 2, we move 2 times. That means how many zeros after the 1? 1, 2. 25 over 100 is typically 0.25. And we know that rational numbers can be written as a fraction where the numerator and the denominator are actually integers. Okay, let's move on to -2. Is this a rational or an irrational number? Yes, grade 9 and grade 10, Kid Luthan. It applies for both grade 9 and grade 10. So if you're a grade 9 learner, you are here. Grade 10 learner, you are here. We are learning together. -2. Is this rational or irrational? Very good. Very good. Very good. I love this. You guys are on top of the man. Sange, Jam Jam. Unomi, Queen Bee, Babes Car Forever. You are spot on. Okay, and I love the reason we said rational because it is a integer. Very good. This is a negative whole number, and under your rational numbers, we also have integers that qualify as rational numbers. Whole numbers also qualify as rational numbers. Natural numbers also qualify as rational numbers. So yes, we are spot on. Number 3. Pi plus 6. Pi plus 6. Rational number or irrational? Or neither? Okay, very good. Irrational. Okay. What you need to do here is, if you are not sure, take your calculator, punch pi plus 6 into your calculator, then after say equal, then you press ST. Alright, and then you check what is the makeup of your decimal after you've pressed in pi plus 6. Pi plus 6, then you press equal, you press ST, and then you check the type of decimal you get, right? And I like that Unomi says irrational and then says non-terminating. Non-terminating and non-recurring. Okay, so these need to be both in the mix. Okay, because they both actually need to be there in order for us to qualify the number as a irrational number. Okay, look at the decimal of pi plus 6. If you have your calculator and you've put it in, maybe one of you can actually write down what the number is. Okay, it should be 6, actually it should be 9,31 something. Okay, 9,14 something. 9,14. You guys can actually let me know what the actual number is, but it's 9,14. It's just that I don't have my calculator with me, but those who are having their calculator, you guys should see it's 9,14, and there's other numbers that are there, but there's no repetition in those numbers after the comma. There is no stop. So that's why we say 9,14 something. There's other numbers, but there's no repetition, meaning there's none recurring, and there's no stop, meaning no termination. So that's why we say pi plus 6 is not rational, but it is irrational. We can't say neither because pi plus 6 does fall into the category of irrational number. Okay, so hopefully Mkhwebu is clarified, okay, that we can't say neither because pi plus 6 is actually irrational. Okay, all right. Okay, I think we are on the same page. Can we move on to the next question? I'm glad you are. Then let's go to our calculator. So that's why I'm saying your calculator will help you. If you are lost as to what type of number this is, put it into your calculator and then check the decimals. All right. If the minute it says maths error, then it means that you need to check at two options, either non-real, because you might have looked at the question and not seen the even root of a negative number. That means non-real. But there's also division by zero, which means undefined. All right. So there are two types of maths errors. Maths error can either mean undefined, that's when you have division by zero, or it can mean non-real, that's when you have a even negative number. Okay, let's look at this one. Square root of 10. Is it rational, irrational, or neither? The square root of 10. Okay, yo, Nomi is quick and on the money. Square root of 10. Is it irrational, irrational, or neither? Okay, and I like the explanation. Irrational because it's non-recurring, so yes. Irrational, and two things. We need to both state those things. Non-recurring and non-terminating. Need to write both, ne? Need to write both as an explanation. You can't just say non-recurring. You must say non-recurring and non-terminating. There's no repetition and there's no stop. No repetition, no stop. Okay? Grade 10 and grade 9. Bales. Both grades. Next question. The square root of negative 16. Rational, irrational, or neither? Neither means not both. Square root of negative 16. Okay, I see what N has said. Let's see what everybody else says. Okay, I see what Sange has said. Cham cham. What does everybody else say? Okay, so this is neither. Thank you so much, Elita. Elita Mkhwebu. I see now you've supported the notion above. Okay, I'm just gonna call you Lita if that's fine. So yes, this is a negative number inside the root, but this is an even root. And what did you say even root is? The even root is non-real. Okay, an even root that has a negative number is non-real. So that's very important. So that's why we say neither. It's not rational, it's not irrational. So that's why we say neither. Next number, the square root of 16. Rational or irrational or neither? Rational. Okay, so hopefully we saw. No, Spare, you can't do that. You can't do that. You can't take out the negative. You can't. Okay? The negative sign is inside the square root. So you can't take it out. So that's wrong. That's incorrect. Okay? No, you can't. Okay? So what we have to then say here is, what is the square root of negative 16? The negative is already in a committed relationship with the 16 inside the square root, so you can't take it out. Right? 16, the square root of 16, I love that you guys say rational, because you should have checked with your calculator, or at least known off the top of your head that the square root of 16 is 4, and 4 is a what? Is a rational number. Simply put, okay, because 4 can be written as a fraction, where the numerator and the denominator are integers. Okay. Remember, the square root of a plus b is equal to the square root of a and b. Yes, that's very true. But what you are saying now is basically you negative 1 times 16. Okay, that's what you are saying right now. Huh? But the square root of negative 1, what is that? What is the square root of negative 1? Okay, remember, you can't take out the negative. The square root of negative 1 will give you a non-real number still. Okay, this is how you would break it down. You would break down negative 16 into the square root of negative 1 times the square root of 16. But then the square root of 16, though it's 4 times the square root of negative 1 will still give you a non-real number. All right, because the square root of any negative number is actually non-real. So this makes this entire number non-real. Okay, so spare. I'm glad that you understand the decomposition of this number, that you could decompose it into this respectively. But then I think with your calculation, you've got it a bit wrong. Okay, the final answer for this will still give you an unreal number if you break this down into negative 1, the square root of negative 1 times the square root of 16. Okay, but that's fine. I'm glad that you could contend that and you could kind of like also have a different thought. That's fine. I love that. Okay, when you are a math student, you should always be thinking. You shouldn't just take my word for it. Okay, let's move on. What about 0? Real, is it rational, irrational, or neither? 0. Alright, sorry guys, I got disconnected there for a little bit. So what about 0? Is it rational, irrational, or neither? Okay. Yes, definitely irrational because it's a whole number, right? Yes. And obviously 0 can be written as 0 over 1, which is integer that qualifies as a rational number. And yes, it's a whole number as well. Thank you so much. It's a whole number, it's an integer, alright? So basically that basically qualifies it as rational. Okay, moving right along. 5 over 0. Rational, irrational, or neither? Okay, you know me, neither. Jesus says neither as well. Babe says neither. Okay, guys, you are spot on. It's neither. But please, it's not non-real, all right? Okay, it's undefined, and there's a difference. Okay, please, when you punch this into your calculator, you get maths error. But this maths error does not mean the same thing as the maths error for non-real. So this is undefined because we say any division by 0 is undefined. Remember, we said that a rational number is a number that can be expressed as a fraction where the numerator and the denominator are integers, but the denominator can never be 0. So if it is 0, then it means that the number is undefined. Okay, so the reason would not be non-real. The reason would be undefined. Okay, remember, non-real applies for when there's an even root for a negative number. Then we say it's non-real. We don't say this is undefined. We say this is non-real. Whereas this is undefined, not non-real. Okay, so let's make that distinction. For a negative number that has an even root, we say it's non-real. But for a fraction where there's a division by 0 or a number divided by 0, we say it's undefined. So there's a difference between non-real, where there's an even root for a negative number, and undefined, where there's a number divided by 0. Okay, so let's make that distinction clear from the get-go. Okay, so those who said neither are correct, but your reason for saying neither must only be undefined, not non-real. So Unomi said neither and then said undefined, non-real. So non-real is incorrect. It's undefined only. Kagiso said neither. All right, but you need to give me a reason. Babeska Forever said neither, but then your reason, non-real, is incorrect. So we say neither for this one, undefined. Okay, different from this one, neither, because this one, the even root of a negative number is non-real. Okay. Okay, next number. Let's look at another number. 0.54321543215432221. Then there's a dot. What is this one? 0.54321 54321 54321, and then we put a dot to indicate that we continue in this fashion. So what is this? 54321 after the call. 54321 54321. All right, so Flowan says rational. What does everybody else say? Babe Scar Forever says rational. And says recurring. Kagiso says irrational. Alright, so this is rational. And why do we say rational? Remember, we said that when after the comma there's a repetition of multiple or single digits. So multiple in this case, because it's 5, 4, 3, 2, 1 pattern. 5, 4, 3, 2, 1 pattern. 5, 4, 3, 2, 1. And there's this dot to indicate that this is continuing on the same pattern. So this is rational. Why? Because this is a recurring, it's an infinite recurring decimal. So this is recurring, repetition of multiple digits after the comma. Okay? So this is rational. So Kagiso claim, remember, irrational numbers are the opposite. They are non-recurring and non-terminating. So this is recurring. Let's look at another one. The cube root of negative 27. Rational or irrational or neither? So Clem says rational. Nomi says rational. Joanna says rational. Okay. So here, when we put the cube root of negative 27 in our calculator, we get negative 3. And the number negative 3 is an integer, which means this is a rational number. Why? Because it's an integer. Okay. And integers fall under rational numbers. Okay, so that's very straightforward to the point. Let's look at another one. 0.793115605835183446 ... Rational or irrational or neither. 0.7931156480518346. Irrational. What does everybody else say? No, me. Irrational, non-recurring, and non-terminating. No, me. So irrational. Okay, I love this. Okay, so this is irrational. Why? Look at the comma. After the comma, what is this? 7931156480518346. No repetition. This number will go on forever. So this is actually, I like what Nomi says. Complete answer. Non-recurring and non-terminating. Okay, that's the full reason. Non-recurring, meaning there's no repetition of numbers after the comma. Okay, it's funny how some people will say, but say, look, there's a 1 here, there's a 1 here, there's a repetition, and then there's a 1 again there. No, guys, remember, there has to be a pattern of repetition. So here there's no pattern of repetition, so that there's no repetition here. Non-recurring. Non-terminating doesn't stop. Look at this ... It indicates that there is other numbers that we don't know about that will be here. It doesn't mean that these numbers will repeat. No, it means that there are other numbers that we don't know, but it goes on forever. So that's why we say it's non-recurring and non-terminating. No stop and no repetition. So that's why we say it's irrational. Let's see, another number. The cube root of negative 9. Rational, irrational, or neither. Cube root of negative 9. Thank you guys for the follow. Thank you for the follow. I think we are approaching 9,000 followers on the page, which is amazing. Those who are joining in as well can go to my YouTube page. YouTube page is called Maths is a Game. Maths is a Game. You guys can help me a lot by actually going to that channel and subscribing, because I don't ask any of you to pay anything for being on the TikTok page, and I run these lessons for free. But what could help me is if you guys actually subscribe to my YouTube channel. Hopefully we can get to a place where that can actually become monetized, and then yeah, it will pay itself. So thank you so much, and I really appreciate you guys following the page. The YouTube channel is also called Maths is a Game. You can go on that and subscribe to that channel. All videos that I finish here, I will post the video that I've just done of this live. I'll post it onto the YouTube channel so that people can go and watch it again and again. You can share it with your friends, share it with your other relatives, cousins, aunties, uncles, call it what you want, so that they can also have the benefit of starting early with the maths lessons for grade 10 and grade 9. Even now during the holidays, and they can be sharp as you guys are. Okay, so the cube root of -9, okay, irrational. Kagiso says irrational. Hopefully you guys put this into your calculator and you saw that it gives you a negative number that is non-terminating and non-recurring. So basically you can see there's no repetition in that decimal that you get. If you put this in your calculator, say equal, press ST, you should get a number that is basically non-recurring and non-terminating. So this is also what? Irrational. And Tlowana gives us the full reason: non-terminating and non-recurring. So good job, Tlowana, for this one, and good job to Naomi for the previous one. You guys are doing amazing. All right? Non-recurring and non-terminating. We write both of those reasons: non-terminating and non-recurring. Okay, the last two. Pi over 3. Rational or irrational or neither. Pi over 3. Pi over 3. Babes forever. Irrational. One irrational. Non-terminating. Okay. So likewise, if you put this in your calculator, you should be able to get a decimal number after you press ST, and you should see that that decimal number is non-recurring, meaning it does not repeat, and it is non-terminating, meaning it does not stop. So yes, okay, remember, Naomi, it has to be non-terminating or and, not or. Non-terminating and non-recurring. Okay, both of those things are in place. Non-terminating and not recurring, and non-recurring. Okay. Yeah, all right. And the very last one for the day, the square root of 9 over 16. Square root of 9 over 16. Rational, irrational, or neither. Kagiso, non-terminating means does not stop. Terminate means to stop. So if you say non-terminate, it means to not stop. Okay? Yeah. Meaning the numbers after the comma, they go on forever and ever, but they don't stop. That's non-terminating. Non-recurring means there's no repetition. As the numbers don't stop, there's no numbers that repeat. There's no pattern of repetition. Okay? So hopefully that's clear for you. Nomi rational. Koketo rational. Tlowana rational. Babes forever rational. Hopefully you guys saw that obviously the square root of 9, you can decompose this to the square root of 9 over the square root of 16, which gives you 3 over 4. This is a fraction. Okay, 9 is a perfect square, 16 is a perfect square. The square root of 9 is 3, the square root of 16 is 4. Alright, remember for division and multiplication, you can break down the square root to the square root of 9 over the square root of 16. Gives you 3 over 4. This is a fraction. Integer, so this is rational. Okay, and if you put in your calculator, you do get a what? You do get a terminating decimal, which is 0.75. So I love that you guys are really getting into the groove of this. Okay, so guys, that's it. That basically is it for today. All right. So tomorrow when we have the live lesson for grade 10 and grade 9, because grade 10 and grade 9 now, I'm going to run these concurrently. All right. Actually, not tomorrow. It will be on Friday. Okay. Because tomorrow I'm going somewhere. There's something that I need to do. But on Friday for the grade 10s and the grade 9s, okay, we can just make it stand at 7 o'clock in the morning for the grade 10s and grade 9, because you guys' syllabus at the beginning is the same. We'll be looking at how to convert terminating decimals into fractions, which you guys saw, and we're going to look at how to change recurring decimals into fractions. That is the next thing that we need to do for the syllabus. Then after that, after we're done with that, we are going to look at two consecutive integers. We're going to look at surds, something that we refer to as surds, irrational numbers, and basically how those surds lie between two integers. We're going to look at that after that, so that is for the next lesson. The next lesson, we're going to look at how to convert a terminating decimal into a fraction and how to convert a recurring decimal into a fraction. Then we're going to look lastly at between which two consecutive integers does a rational number lie, how to identify the two integers where a particular irrational number lies. Okay, so this was grade 10 and grade 9, guys, simultaneously, grade 10 and grade 9. Okay, and this is basically the end. I am going to post this video of this live session onto my YouTube channel, so you guys can go on there and you can watch that video. If you missed out on the lesson for grade 10 and grade 9, people were asking me, when am I going to do grade 8? Guys, I don't know, because I have a very racist schedule. My schedule is not really fixed, in the sense that there are things happening here at home. I can't unfortunately fix myself to a specific time. So when I do a live again during the course of today, it will be for grade 8. And then hopefully I'll try and also squeeze in grade 11. But grade 10 and 9 is sorted for this morning, and I'm going to post the video of this live session onto my YouTube channel as soon as I'm done with this particular session, which is like now. Thank you so much to those that joined. I saw Unomi was very active today in the comment section. You did a phenomenal job. I can see you guys are really getting a grasp of the content. Babes Forever was also amazing. Utlowana was amazing. Koketo just joined in, but also just participated very nicely. Ukachis was phenomenal as well. Participation was just off the chains. I like the fact that people were asking questions, people were engaged, people were really trying to get clarity. If there was something that they did not understand, the minute they did not understand, they actually asked the questions in the comment section so that I can clarify if there's something that you don't understand. So you guys, really appreciate you. I hope you guys can continue joining in the sessions. Alright, so grade 9 and 10 on Friday, I'll be doing another session at 7 a.m. You guys can join in the session at 7 a.m. on Friday. That's where I will be picking up from where I left off. If any of your friends that you know may have wanted to join the session but don't know about the session because they don't know about the TikTok page, you can invite them to follow the live creator here on TikTok, so that when I do go live again, they can actually have the benefit of joining in the sessions. For grade 9 and 10, I'll be joining again on Friday, and then I'll announce, as like I said, for grade 8 today. I may do a live today later on, but like I said, it's a bit tricky because of my schedule and how things are here at home. But I'll try and do my best. But please do go to the YouTube channel, Maths is a Game. The YouTube channel, Maths is a Game. If you missed out on Monday's session, you can go there and actually go and check out what we did on Monday for grade 8s, for grade 9s, and grade 10s. And I'll be uploading this session for grade 9 and 10 that I just did now onto the YouTube channel as soon as I'm done with this live. But thank you very much. Lots of love. Hope you have a good day and continue practicing the maths. Maths is a game. The more you play it, the more you get familiar with the rules, then distinctions just come, guys. And this is what we're doing here. We're trying to prepare us very early so that level 7 next year, term 1, can be a reality. 100%, if you want, can be a reality because it's possible. All right. Thank you so much, and I'll see you guys again. Bye.